So the title is Equivariant Derived Categories. So let X be algebraic variety. C algebraic group. So what I want to do, I want to describe some tool how to analyze the geometry of an object X modulo G. How to think about this? Yes, GS, excuse me. Yes, otherwise it's a little difficult. So first I want to discuss why do I care? And this is connected with something which Misha Gromov told in his first lecture, namely how to find some interesting algebraic variety. And if you think about it, I thought about it, and I realized that there is exactly one way to do it. There are not many ways, there is one way, namely as a modular space of something. So what does it mean? That we define some, consider some, find some category M such that objects of this category M are parameterized by finite number of objects, parameterized by finite number of parameters. Okay, and then we declare that we want to consider algebraic variety Z, which is just isomorphism classes of objects of M. Iso of M, this is a set of isomorphism classes of objects of M. So this is a rough definition. The problem, so this is how usually you construct new algebraic varieties. The problem with this definition is that this is not really an algebraic variety. For the following reasons, there may be some objects in M which have inner automorphism, non-trivial inner automorphisms. Non-trivial automorphisms. So this means that that Z is not really an algebraic variety. Some points have, to each point you assign some additional groups, let's say inner symmetries. So, and of course you cannot ignore this if you want to study this kind of problem and just declare that you consider just as a set, you lose information. So one of the standard ways to work with this problem is that you consider what's called modular space. Namely that you consider some part, instead of all category M, you consider just part of objects, so-called stable objects. Stable or semi-stable, doesn't matter. And for them, this automorphism group is trivial. And then you consider part Z stable. And so this table is actual algebraic variety. Frankly, I never was able to understand the meaning of this procedure, where you throw away, so to say, interesting part and consider only this. But that's nevertheless some standard way to do it. So now let's consider, so if, so one has to, from my point of view, one has to actually face this Z, this isomorphism classes of M, and to describe the geometric structure of this object. So let me give an example. Just another talk. So example, we consider M to be category, so suppose some S is algebraic variety, for instance, usually curve, so C is a curve. M category of 5-dimensional bundles over C. Consider bundles of dimension 5. And then consider isomorphism classes of this. So this will be, so it's clear that this will be parameterized more or less by finite number of parameters. And this is the, so we consider Z is isomorphism classes of bundles. So now, if you consider stable bundles, if you form some isomorphism classes, if you form some algebraic variety, but we want to analyze structure of geometric structure of the whole this thing. So such objects are called the standard names. No, stack, algebraic stack. And so in principle we would like to know how to analyze the geometric structure of algebraic stacks. So algebraic stacks contain algebraic varieties. And as Misha pointed out, that if you want to find any interesting algebraic varieties, then you immediately get in the world of stacks. So you cannot avoid this. So I will consider, I want to explain that. So the one typical example of stack is this X modulo G. So namely, I can think about this in the following way. I consider category M such that objects of M are just points of X. And morphisms of M are pairs, point of X and element G, which I consider as morphism from X to Gx. And so if I consider, so if isomorphism classes of this category M will be just X mod G, just as a set. But each element will remember, each point will remember also its stationary subgroup. So, so that's why I want to do it. And so, so this will be simplest example of a stack. And I want to what I want to do, I want to describe some tool how to discuss geometry of this space. So which will be interesting even in the real case when X is a point and G is some nice group. So how to describe the geometry, how to talk about geometry of this space. So first of all, when I talk about geometry, then I should explain how to think about geometry. For instance, if X is an algebraic variety, so how to think about geometry of X? What does it mean? So by now, I think the standard way to think about this is the following, that we consider shifts on X. Consider some shifts on X, category shifts on X. One moment. So there are different geometries. So you can consider, for instance, so different geometries. Namely, you consider coherent or quasi-coherent shifts. Or you can consider shifts so topological, so when X is a complex manifold, or étal, So you consider some notion of shifts. And different notion of shifts give you different geometries of which you want to consider. So if you have an algebraic variety, then you can consider it either from point of view of coherent sheaves, or you can consider from, for instance, the Tal point of view as, let's say, following value as somehow topological space. So now, of course, so I claim that geometry of algebraic variety is given by first some category of sheaves. But also, this is clearly not enough. You have to have functors between different categories. Namely, if you have morphism x into y, then you should have functors something like sheaves of y to sheaves of x, functors of direct image from sheaves of x into sheaves of y, and so on. So, for instance, so if you have, for instance, coherent sheaf on x, and then I have a point in x, then I can, embedding of this point, I can consider this sheaf and consider inverse image of this sheaf at this point. It will give me a fiber of this sheaf at this point. So this allows me somehow to connect these sheaves which are floating somewhere in space to actual geometry of x. So first ansatz which I want to make that the geometry of algebraic, when we talk about geometry of algebraic variety, we talk about this kind of thing, that we have category of sheaves and have different functors between these categories.
Complex or tangent bundle, is it a part of geometry?
Yes, sure. No, so can be expressed in this language. So now, of course, very soon one finds that in order to define these functors, one has to pass to slightly larger category, which is called derived category. So we have what's denoted d of x, which is derived category of sheaves of x. So now what is derived category? So in formula, so object of derived category in sheaf of x is a complex of sheaves F, I plus 1, and so on. And we consider them up to quasi-isomorphism. Up to quasi-isomorphism. Now there's two complexes which are quasi-isomorphic. We declare that they are the same. And this is our category. So we have, so our original category is embedded here. So this category is abelian. This is not quite abelian, but it has some additional structures which make it look like, which allow to work with it even better than, sometimes better than with abelian categories. Okay. So now what I want to do, I want to define these objects, sheaves, and derived category of sheaves on X mod G for this stack X mod G. I want to describe how to think about this. So to think is it to reduce it to the, I assume that I know everything about algebraic varieties. And then I consider new geometric object, X mod G. And I want to explain how to compute, how to express, mostly I'm interested in this category, in terms of corresponding categories for algebraic varieties. So here is some difference. The idea is that for usual varieties, you can, to some extent, ignore derived category, because we saw that, after all, element of derived category somehow is complex of shifts. So there's not too much difference, it seems. Here, the situation will be different. So we'll see that in typical example, this category is just very simple, just very, very small. And this category is much more interesting and large. So you should work with this category if you want to get anything. You should work straight with this category. Okay, so now, so once more, what is the game? That I assume that for algebraic varieties, I know what is d of x. So it may be either category of derived category of coherent shifts, or derived category of Vital shifts, or derived category of D models, and so on. And I want to explain what is derived category for this case. So now, of course, this case is just a special case of these algebraic stacks. So in principle, as I understand, so for some formally smooth algebraic stacks, one can also define these categories. Sasha Berenson knows how to do it, but his construction is much more involved. So I want to explain that in this case, it is straightforward. And I want to try to present some applications. Okay, so suppose I have this object, x mod g, and I want to define its derived category. So first I make an ansatz. Yes. So first I say that x, suppose x is a free space, a free G space. Oh, that's P. Is a free G space, and P bar is equal to P mod G. So then I want that derived category. So this derived category, excuse me, I will introduce a definition. So this derived category, which I want to define, is called equivariant derived category. And I will use notation dg of x. So it's equivariant derived category of x with respect to the group G. So instead of this notation, I will use this notation. So then, equivariant derived category dg of x is naturally isomorphic to the derived category of quotient space of P. Excuse me. So this is ansatz. So in case of free spaces, free actions, when you don't have any stabilizers, then you should just pass to the quotients and forget about it. And I can give an explanation of this because I described this notion of stacks, but there is, of course, a relation of there is a notion of equivalence of stacks. So some of stacks are equivalent, and in this, so this stack P mod G, in case when action is free, is just equivalent to the trivial stack, to the stack P bar, which is a set with all morphisms trivial. So for this reason, we want naturally that we want the derived category, in fact, is defined for stacks. So we have this thing. Okay, so then it turns out that from this we can, in fact, very easily understand what should be the notion of this derived category. Because let's make an analysis. So analysis, meaning like in elementary geometry, we first analyze the problem. So suppose we have a sheaf, an object, whatever, an object f in this equivariant derived category of x. Consider a resolution of x, which is a morphism of G spaces mu p into x, where p is free G space. So such thing we will call a resolution of x. So resolution of x is morphism onto x of a free G space. We usually always assume that mu is smooth, epimorphic, and so on. Epimorphic and some other nice properties. So if you have such a resolution, then we can consider corresponding object, inverse image, mu star of f will be object in equivariant derived category of p. We can lift. So we have this morphism. We have equivariant element of equivariant derived category here. We assume that all equivariant guys satisfy the same properties as usual. So we can lift it, consider its inverse image on P. But this is nothing else, by our ansatz, this is nothing else than element of derived category of P bar. That's something already which we know, because this is just an algebraic variety, and we know what we are talking about. So hence, let's denote this thing.
P bar doesn't remember G, right?
Yes. P bar is just an algebraic variety.
So D
And this is just usual derived category.
G is gone now, right?
What?
G is gone.
G is gone. Yes, that's the idea, that G is gone here. So let's denote this F nu. So this will be D of P bar. So what's the result of our analysis? Starting with object F in this mysterious equivariant derived category, we constructed for any resolution mu p of x an object f nu in D of P bar. So something which we already understand. Of course, these objects are connected to each other in a natural way if you have morphisms of resolutions. So now natural thing is to define. So now let's define definition. So an object f in dgx is a collection, a compatible collection of objects f nu in D of P bar for all resolutions mu p into x. So this is this will be definition. The question is, of course, how to work with this definition. It will be here in a moment. So when do I start, Tima?
You're talking only for 25 minutes.
Okay. Okay, so now the question is not to show that this category has, in principle, I can define this category, I gave a definition of this category, but in order to show that it has nice properties, for instance, like usual derived category, we should, in some sense, to try to find the universal resolution. And it turns out that it exists, but not always. So I can consider a case when G is, for instance, elliptic curve. So in this case, I cannot construct my theory. Somehow it's not good. And again, Sasha Benison has some examples when, in some sense, you can this is a bad case. So
Could you explain?
This example.
I think it would be very useful to know what is.
No, for instance, so let's give examples, but then I will refer to the decomposition theory, which is not. So consider, for instance, action of E on itself, and then we have natural morphism of E mod E into point mod E. This is a proper map. So if you consider constant shift here, then if the decomposition theorem is true, and that's what we want to expect, then its direct image here will be sum of its cohomologies. Now the problem is that this thing is trivial. This is just a point. This stack is just a point. So its cohomologies is trivial, while this thing is highly non-trivial. So hence the cohomology of this cannot be a direct summand of cohomology of this. So it means, for instance, that decomposition theorem doesn't work. So in general, somehow I don't believe in this case. It's a reasonable theory. Sasha can give definitions. That's a different story. But I want to consider another case with G is linear algebraic group. So in this case, I can describe this thing in some more straightforward language, namely G linear algebraic group. So I can assume that G lies in GL KC. Then I want to construct some free G spaces. Natural space which comes to mind is the following, that I consider the space a linear space. Find a linear space V of large dimension, very large dimension, and consider Stiefel variety, Stiefel K of V. So this is a set of vectors V1, Vk in V which are linearly independent. So consider this space. Then on this space we have the action, free action of the group G. So Gx freely on this. So so this is standard, of course, construction of universal bundle. So G acts freely on this Stiefel variety. That's first. And second thing is that, which we'll use, that this Stiefel variety is almost contractible. This Stiefel variety is embedded to V to the power k and has complement of very high codimension. Codimension more than n. So it's almost, from any homological point of view, this variety is almost coincide with this one. It's also okay. I will. So I will explain what it is okay for, and then it will be clear. So, okay, and so now consider the following resolution. Consider P to be equal Stiefel K of V times X. So this is a free G space. And I claim that this resolution is almost universal. So let's call that resolution is universal if object, so resolution mu P is universal if object yes, mu is a projection, of course, here. Mu is X projection. What? No. No. So P naught here. So resolution mu naught P naught is universal if object mu naught of F allows to reconstruct objects, all objects, F nu for all resolutions. Okay, so I claim that this resolution which we constructed is not quite universal, but it's almost universal. Namely, it has the following properties. If my F is, I remind, is a complex of sheaves. As any complex of sheaves, it has homologies in some dimensions. So let's suppose hi of F equal to 0 for I outside of some interval. We have some small interval in Z such that all cogomologies are concentrated inside this interval, for instance, from 0 to 10. And then I claim that if n is sufficiently large, then for all sheaves F with this property, this resolution will be universal. And let me just describe. So this is both in category of coherent sheaves and in category of topological sheaves. Let me describe the geometric meaning of this procedure. The geometric meaning depends on the following lemma. So consider this projection P into X nu. Then for any F in X, in the category of X, with this restriction homology, we can reconstruct F in G invariant, effectively reconstruct F in G invariant way from H, which is mu star of F. So just I want to explain the lemma which is behind this universality property, that if I have sheaf F here and I lifted it to P, then I want to reconstruct back this sheaf. And the idea is the following, that here I have morphism into Vk cross V. So here I have nu prime. And let's consider now the sheaf G star of H. So here, suppose I have sheaf H here. I know that it came from some sheaf here. I want to reconstruct this sheaf. So the procedure is the following. I take this H, I consider its image here. And then I claim that this image is almost isomorphic to nu prime star of F. Namely, it's isomorphic up to terms which cosmologically lie somewhere far away, shifted by n. So if I just take this thing and consider truncation of this, then I will reconstruct this guy. And then taking here zero section, which is G equivariant procedure, I will reconstruct F. So in this way, in just a very explicit way, starting from H, I will reconstruct F.
You need Gx in combination with
Gx everywhere here. So my construction will be completely.
But someone just said you forgot about G. Describing it.
No. So once more, I'm explaining what is behind. I formulated this property, that this special resolution has this almost universal property. So when you start proving this, then you will immediately reduce to lemma like this. So I don't want to go into details, but and this is just what I want to say, that this is true in both in topological category and also in category of coherent sheaves, because if you consider the same thing, if you consider sheaf O on this variety and you consider its direct image into V, then it will be O plus something in very high dimension. Okay, so that's so. Dima, how much time do I have?
5 more minutes.
Okay, 5 minutes.
No, 45 minutes.
How many?
Well, 45 minutes will be in 5 minutes.
Okay. Okay, so now I want to so this is the definition. Now I want to just to consider some couple of examples which I find amusing. So first is that I want to consider some simplest possible cases. Namely, I want to consider derived category of point modulo G. G, for instance, is JFK. So this is some concrete category. And first thing which I want to do, I want to have explicit description of this category, just plain algebraic description. So it's more or less clear that this is somehow connected with equivariant cohomology of J. And so let's consider a algebra of equivariant cohomology. Yes, yes. So this is in case of topological sheaves. So this is topological category. So in coherent case, it will be rather trivial. So consider algebra of equivariant cohomologies. So it is just I consider for simplicity just complex homologies. So it will be xk graded ring I. So then it turns out that this category can be described in the following way. Namely, we'll consider let C be the category of differential graded A models, finitely generated, for instance. And then D will be C moduli quasi-isomorphisms. Isomorphisms. So I consider this algebra C of DG A models. A is this algebra, and this is differential graded models. So as usual, differential is of degree 1, and so on. And we consider this modular quasi-isomorphisms. So then the claim is that this category is equivalent to this topological category. So in this case, we can compute this category explicitly. So next thing is some variation on this example, that if I have, so this is 1, this is 2. So suppose X is transitive G space. So X is equal to G mod H. Then, of course, dg of X is the same as dh of a point. From the point of view of stacks, it's clear that they give the same stack. So we can compute it in a similar fashion. And so next interesting example is that suppose X has finite number of orbits. So then this category dgx should have some explicit algebraic description in terms of these orbits and some relations between these orbits. So I know several cases which are worth studying, and some of them are done, and some of them are not. Just to give, so the problem is to give explicit description of this category. Yes.
Simply, you reduce the case when it's transitive to the case of a point.
Yes.
If the case of a point, you only told us the answer if G happens to be GLK.
No, this is the same. That's the same. So for all groups.
Classifying space as the group.
Yes. So yes, you always take classifying space. Important thing is that this equivariant homology ring is always free algebra. So then, if it wouldn't be free algebra, then there will be problems. But since it's free algebra, there are no problems. So examples which I know are the following. Examples, first G is a torus, and X is toric variety. So, for instance, X corresponds to some polyeder, to a polyeder delta with integral vertices. And then, so orbits of G correspond to faces of this polyeder. And so then it turns out that, so this is most of what I'm talking is joint work with V Polyarums. And so, for instance, he has proven that you can describe, in this case, dg of X, can give a similar description, can describe in terms of sheaves, differential graded sheaves of A models on finite topological space X mod T. You can consider X mod T, this will be just orbits. They will have some funny topologies. They're just faces of this delta with natural topology. And so in terms of this topological space, and for each delta, of course, you have to know what is the stabilizer group of this delta. You can explain explicitly how to construct this category. So in general, I should say that I consider these categories as some funny extension of the notion of equivariant cohomologies. So this, for any X, you assign not a graded algebra like in equivariant cohomology, but you assign something more interesting. Just some category, but in these cases, at least when you have finite number of orbits, these categories are somehow very mild. You can describe them. They contain finite number of parameters. Yes. My time is up. No, so
I was going to ask if you could do the case of G acting on itself by conjugation.
No, I didn't say. No, this is one of, so maybe that's one example. No, I think that next interesting example is G acting on square Flock variety. You consider Flock variety of the group G. Consider the action of G on here. You have finite number of orbits. So in this case, we know that since this product of two things, then we'll have some kind of algebra in it. So we'll have some interesting category with standard product, so something. So now, so next thing is we want to. Okay, so just one more thing, and I want to just to say. So, so another thing which I think is interesting here is extension of first example. So consider G is equal to T X toric variety. But then consider category of coherent sheaves here and try to analyze it. So in toric variety, we have natural filtration. So we have U0, U1, and so on, where U0 is an open cell, which is isomorphic to T. U1, you add all faces of codimension 1, and so on. So let's try to describe some one-dimensional sheaves on X. On U0, anything is just trivial. If you consider G equivalent, T equivalent sheaf on T, it is just constant. When you extend to U1, then each face gives you, in order to extend it, you should write down an integer number, which is action of corresponding subgroup. So it's a very explicit description. So,
I think that your inclusions should be in the opposite direction. Your note should be embedded.
yes, you're right. Excuse me. Here, X. You notice, yes, I want to extend. So this open orbit, here add something, and so on. So in order to, so I want to describe just one-dimensional sheaf. So I consider trivial sheaf here. I extend it here, and this gives a collection of numbers, nu sigma for all faces of codimension 1. And then I want to extend it further. So there is one way, one trivial way to extend it, just take direct image. Since we killed all the things of codimension 1, this direct image will be coherent. But the idea is that it's a long way. It's, for instance, it's not compatible with duality. In all these things, which I somehow haven't mentioned, the important thing is that everywhere here you have duality. So in this case, you have third-Grothendieck duality. So now the claim is that there exists some intermediate extension, which is not a sheaf, which will be equivalent element of equivalent derived category. So without language, I cannot even describe it, what I'm talking about. So the claim is that there exists some canonical intermediate extension, which, let's say, reminiscent on intersection cohomology extension of McPherson, Garevsky, and Dring. And somehow this thing, after you have this extension, you can compute its earlier characteristic, and this will tell you this is somehow connected with estimate of the number of integral points in this polyeder. Okay, I will. So this is quite responsible. Just I'm saying that there exists this interesting thing which I don't really know too much about. I can prove that there exists such extension, but that's more or less all. Okay.
Yeah. Did the question?
Yeah.
I have two questions. So the first question is, I probably just missed. In the description of the equivariant category for GLN, this is the category of what kind of sheaves?
Topological.
Topology. If I take equivariant derived category of this quotient of the point with respect to a G, but then I take the coherent sheaves, do I get the derived category of representations of G?
Yes, I think yes. So for semi-simple loops, that's definitely true. I think that's true. So in this case, it is not trivial, and not interesting, because in this case, so this derived category is derived category of equivariant sheaves. For instance, we see that in this case, it's just not true, because equivariant sheaves here, so in this example, equivariant sheaves will be just trivial, just trivial sheaf, nothing else. But the derived category is rather large. Yes.
The second question is, can I in general describe any object there as a collection of sheaves, of complexes of sheaves on X cross G to the power n for all n, together with some coherence condition?
No.
Coherence.
No, you cannot do this. No. So, no. So once more, there is. Let me tell. So there is one. So essentially, what I will use this as an opportunity to say some philosophical remark. So, as we saw, that essential main thing of this construction was explicit realization of the BG. Now we know that there are two explicit realizations of BG. One is what I used, for instance, for JVM, just quotient. And another is Milner's construction, where you construct some simplicial set. So essentially it means that you consider something like sigma, just sigma naught, union sigma 1 times G, union and so on, sigma 2 times G squared, some union of this thing. So the difference between these two constructions is that this is clearly not a manifold with any definition. Well, this construction, which I used, is a manifold. So as a result, I can define as the duality, which is important thing here. So what you're proposing, so one can give the definition using simplicial things, but then it's difficult to work with duality. So I should say that Sasha does have a way to handle this problem.
But in principle, you can define this category in terms of this simplicial model.
Yes.
Why cannot use any given resolution, just using descent, appropriate couple of state?
What?
You have embedding of your categories and full subcategories.
Yeah.
This is a trend function, right? But general losses should be distinct in terms of percentage. It's different down.
No, so here's question that in derived categories, difficult to write down descent data.
Yeah, but it's high on purpose function.
What?
Responsible.
Yes. Yes, so this is connected with what? Yes, so that for shifts you can just write down descent data if you want to define equivariant shifts. If you want to define equivariant objects in derived categories, then descent data are not enough. I don't know how to do it. In some sense, all this. Okay, so all this construction was in order to give descent data. So for instance, if P is n universal resolution, just in the way which I described, then if you give descent data, then you can define f by descent data if f is supported in degree n. So in some sense, if you want, you can avoid these things, just to give definition in terms of descent data for resolutions which are sufficiently acyclic. But for instance, standard Milnor resolution is not good for these purposes.
I suggest
Okay.
we stop now. And when is the next talk?